Hey math enthusiasts, I'm here to go over some notes on inscribed angles and polygons today with you guys. So we have our definitions down below. As far as an inscribed angle goes, it's a little different than the central angle that we talked about from the last section. Central angle came from the center of my circle, where the vertex was in the center. Well, for an inscribed angle, the difference is that the vertex is now on the circle. So essentially my angle has now been stretched all the way across my circle. All right, and obviously you can see these two sides, AD and BD, are actually going to be chords in my circle. Now, when I draw an inscribed angle, what happens is it opens up to an intercepted arc. Okay, so here's my inscribed angle, angle ADB, and it opens up to this arc AB. That's my intercepted arc. Now, what we learned in the previous section is that the central angle and that intercepted arc have the same measurement. Well, that is not going to be the case anymore for inscribed angles. Now, my next term, inscribed polygon. All right, similar to an inscribed angle where you have your vertex on the circle. For an inscribed polygon, it just means all the vertices that make up my figure are going to be on the circle. So let's say I'm drawing an inscribed triangle, then my three vertices that make up that triangle are going to be on the circle. So there's my inscribed polygon in red. Let's say I want to do an inscribed quadrilateral. I would just add one more vertex. There's my inscribed quadrilateral. The last term from this section is a circumscribed circle. So it definitely relates to an inscribed polygon, but for a circumscribed circle, instead of talking about the polygon inside my figure here, this triangle or square, what I'm referring to is actually the circle that goes around that figure. So here's the circumscribed circle, if I can trace them a little bit neater. All right, so it's just pretty much a circle that contains all the vertices of the inscribed polygon. So you have the circumscribed circle in red, and then the inscribed polygon in blue inside the circle. So as for my first theorem, the inscribed angle theorem. All right, so what I'm saying is the measure of the inscribed angle. So now I'm talking about angle D inside my circle, so made up of these two chords, and how it relates to this intercepted arc. Now, as I was saying earlier, for a central angle, it would be the same exact measurement. If the central angle was 150, I would know that the arc would be 150. But in this case, that's not going to be true anymore, because obviously I can tell that inscribed angle is going to be smaller. So let's say the arc is 150. I know that this inscribed angle is actually going to be half the measure of the intercepted arc. So in this case, I'm saying that the measure of angle ADB, so the inscribed angle, is going to be equal to half the measure of arc AB. There's my arc symbol. So for my first couple examples, I'm looking for either an angle or an arc measure. So for the first one, I'm looking for the measure of angle BAC. All right, well, I know it opens up to this intercepted arc, 158. And because it's an inscribed angle, I know that it's going to be half the measure of that intercepted arc. So the measure of angle A is going to be 79 degrees. For the next one, now you're actually worried about finding an arc measure. So I'm worried about finding the measure of arc BC, which is formed from this inscribed angle, which measures 76. Well, in this case, since I have the inscribed angle, I'm going to do just the opposite to figure out the measure of the arc. So I know the measure of arc BC is going to be 152. For the next problem, once again, I'm looking for an angle measure. So I'm looking for the measure of angle A. Appears to be an inscribed angle. Now, let's focus on what we're given. I'm given the measure of angle BOC, which is a central angle. which tells me right away that this arc BC, has to have the same measurement. It's going to be 132. Now, as I said, I got to focus on finding the measure of angle A, which is an inscribed angle. Well, the intercepted arc for angle A is 132. So all I have to do is take that 132 and split it in half to figure out what my angle measure is. So in this case, the measure of angle A is going to be 66. For this last problem, once again, I'm looking for an arc measure. I'm looking for the measure of arc AB. Well, before I get to that, let's just focus on what I'm given in my picture. So I know that this inscribed angle, angle BAC, is 27 degrees, and it opens up to this intercepted arc. So I know right there that that arc is going to be double the measure of the inscribed angle. So I know that arc is going to be 54 degrees. Let's make that 5 a little better, 54 degrees. Then, if you want to, you could fill in this central angle, which I know is going to be the same. Now, as I said, I want to focus on finding the measure of arc AB. Well, what I notice in my picture is that AC right here is a diameter, which tells me that this entire arc right here is going to be a semicircle. All right, I know that whole thing is going to add up to 180. Well, I already have 54, so if I take that away, I'm left with 126 for arc AB. The next theorem in our notes deals with two inscribed angles in our circle. So in this case, I have angle D, that's an inscribed angle, and I have angle C, which is an inscribed angle. Now, the thing is, both of these open up to arc AB. So the blue inscribed angle opens up to arc AB, and the red inscribed angles arc opens up to, the red inscribed angle opens up to arc AB. Well, it really doesn't matter what the measurement of arc AB is. Let's say it's 100 degrees. Therefore, I know that these two inscribed angles have to be congruent. That's all they're saying here. If they open up to the same arc, they have to have the same measurement. So for the first example, all they want is two pairs of congruent angles. So let's focus on this inscribed angle. Angle S opens up to this arc. And then angle R opens up to the same arc. Both of them open up to arc PQ, so therefore I know that angle S must be congruent to angle R. Now I can go back and try to find another pair. All right, well, let's jump to the other side of the circle. So let's focus on angle P instead, which opens up to arc SR, and then angle Q instead, which opens up to arc SR. They both open up to the same arc, so angle P must be congruent to angle Q. Next example, I'm just looking for the measure of angle T. So angle T, it's an inscribed angle. It opens up to arc RS. Well, in my picture, it looks like angle Q is an inscribed angle that opens up to arc RS as well. If you really want to, you can solve for this arc. I know it's going to be double the measure of the inscribed angle, so I know this arc is going to be 62, and then if I go back and focus on the inscribed angle, I know it's going to be half the arc measure, which means it's going to be 31. Obviously, based on my theorem, I know those two are going to be congruent. Next example, I'm looking for the measure of angle A. So let's highlight this entire angle. Looks like an inscribed angle, and it opens up to arc BC. So let's see if I can figure out anything else about arc BC. Well, it looks like B and C also connect to this inscribed angle. All right, well, both of them connect to the same arc, so therefore the measure of angle A must also be 32. Next example, now I'm looking for an arc measure. So I'm worried about this arc up top, BC. Now, unfortunately, I don't have any inscribed angle that opens up to that arc. Okay, I do have a couple chords that touch it, but no complete inscribed angle. So what I'm going to focus on finding is the other arcs that I'm missing right now. Okay, so let's focus on this one right now. Given an inscribed angle right here, angle C, 34 degrees, it opens up to arc AB, so I know it must be double the measurement of the inscribed angle. So right now I know that arc BA is going to be 68. Okay, let's see what else they gave us. Now, the other arc I want to get is arc CD right here. Well, if I'm going to get that, I'm going to need to figure out this inscribed angle right here. Okay, so what I'm going to try to do is focus on this whole triangle down here. Now, I'm given the 124, but I'm going to need more information in that triangle. Well, if I focus on this angle, it's an inscribed angle. It opens up to this arc, which is 68, and this angle opens up to the same arc, which is 68. So I know right away that angle is going to be 34. So at this point in this little triangle, I have 2 out of 3 angles. I got 124, I have 34, which together is going to give me 158. Now, as I said, what I really care about finding is just that one angle all the way on the left-hand side. So I have the 34. I'm really just worried about finding this angle. Well, as I said, I know all these angles in my triangle are going to add up to 180, which tells me that that final angle in there, right here, is going to be 22. So now I can actually go back. We'll erase some of this, clean up my picture. So what I wanted was the 22 right here. It opens up to this arc from the inscribed angle, so I know this is going to be 44. So at this point, I have arc BA, 68, I have arc AD, 128, and I have arc CD, 44. So what I'm going to do is I'm going to add up all those pieces that I do have. 128, 68, 44, which is going to give me 240 degrees total. Now, in this case, I've almost covered the whole circle except for BC. So the last thing I'm going to do, 360 for the full circle. We'll take out the arc that we do have, 240, which is going to leave me with 120 for BC. For this third example, I'm just looking to solve for x. So it looks like this expression is pointing at this inscribed angle, 2x plus 11, and then the 4x minus 3 is pointing at this inscribed angle. Well, it looks like both of these are opening up to the same intercepted arc. So I know right away that they're inscribed angles and their measurement is going to be equal. So I can set up my equation, then you can go through and solve for x. So in this case, x is 7. Our next theorem still deals with inscribed angles. Now in this case, they're specifically talking about a right triangle drawn inside a circle. So it's an inscribed polygon. So in my picture over here on the right, here's my right circle, triangle ABC. Here's my right angle. Now, the thing is, if that's a right angle and it's an inscribed angle, it means that the intercepted arc that it's going to open up to has to equal 180 degrees. And if this is a semicircle, it means that this side of the triangle must be the diameter, has to go through the center. All right, and that's essentially what they're saying right here in this theorem. Now, the second theorem is still dealing with an inscribed polygon, but now I'm talking about an inscribed quadrilateral. Let's take a close look at this picture. So in this picture, I have this inscribed angle, angle D, which opens up to this arc. Looks like a minor arc. And then on the other side, across from it, you have angle F, which opens up to this whole arc here. Now, the thing is, I don't know any of the arc measures, any of the angle measures. Obviously, the blue inscribed angle opens up to the blue arc. The red inscribed angle opens up to the red arc. Now, I do know that this arc all the way around is 360 degrees. All right. Well, I know that the inscribed angle measures in here have to be half the arc measure. So if I put these two inscribed angles together, if I add them up, I know they're going to equal 180 because they have to be half the arc measure that they open up to. All right, and that's what this theorem states. So in this case, I'm saying that those opposite angles, like for example, angle D and angle F, together they're going to add up to 180. So that works for angle D and angle F. It also works for, obviously, angle E and angle G. They would both be considered opposite angles in my quadrilateral. Which brings us to our first example. I'm trying to solve for both variables here, both y and x. Now, as I said, based on my previous theorem, the inscribed quadrilateral theorem, I know those opposite angles, like for example, angle P and angle R, they're going to be supplementary. I know they're going to add up to 180. So in this case, what I can do right away is just set up an equation. I know that 63 and 3x together is going to equal 180. So I end up with 3x equals 117, and x is going to equal 39. As for my other opposite angles, so obviously that'd be angle S and angle Q, I know they're also going to add up to 180. So now I can set up the equation for those two. 4y minus 1 plus 65 equals 180. So I'll move all my constants to one side, which gives me 116. So it looks like y equals 29. Now for the next problem, I'm looking for three variables, x, y, and z. Now let's get started with x first. So x is inside this inscribed angle in my circle. And I know based on my theorem about inscribed quadrilaterals is that x and z together are going to equal 180. Well, that doesn't help me right now because I don't have either of those measurements. So instead of focusing on x and z together, let's just focus on x. Because x opens up to this intercepted arc, which is 108 and 75. So that's going to give me 183 degrees together. Well, I know that the I know that the inscribed angle is going to be half the measure of the intercepted arc. So I'm going to do 183 and divide that by 2, which is going to give me 91.5. Now I can go back to my equation up here. So I said x plus z equals 180. Now I know 91.5 plus z equals 180. Okay. So after I subtract 91.5, I'm left with z equals 88.5. So I've got z, I've got x. Last thing I need is y. So I have a y here, 2y, and I have a y over here, this 3y plus 5. Well, it looks like they're opposite angles in my quadrilateral, so what I can do is I can take those two expressions, add them up, and set them equal to 180. 3y plus 5. 5y equals 175, so y equals 35.